Hello, and I want to welcome everyone to the Geotech Lab here in DKIT for the Triaxial compression test, which is today's geotech experiment. Now, the Triaxial compression test, as the name suggests, applies stress or pressure to soil on three different planes or axes. So if we take a look at the apparatus behind me, and we have a sample already set up. Here's one I prepared earlier, you could say. So here's the triaxial cell, and the cell is perspex, you can see through it. Inside there is a sample of soil, but it's enclosed in a rubber membrane. So this is the rubber membrane which is used to isolate the soil from the surrounding water, so the soil is actually tested in a dry condition. So what kind of soil are we testing? The soil we're testing today is a dry sand. I hope you can see that there. Dry sand, which I've already prepared as a sample. I'm going to show you later how to prepare a sample for the triaxial test with a dry sand. Now, to explain a bit about the test, there are in fact three types, in fact more than three, but three major types of triaxial compression test. The test we are doing today is the quick undrained triaxial compression test. And this test is suitable for dry materials like the sand we're about to test, or for an undrained test on a clay sample. Undrained means that water can't drain out of the sample. So the quick undrained test is good for determining the friction angle of, as in this case, a coarse sand. The next type of test would be a drained test. A drained test is normally carried out on a clay type material, a cohesive soil, and during the test water can drain freely from the base of the sample as the sample is loaded. And there's a third type of test, in fact there's a whole series of other tests, but a very important test is a test using effective stress parameters, and that's where we conduct an undrained test like this one on a clay soil, and we measure the water pressure inside the sample, the pore water pressure. Now if we measure the pore water pressure inside the sample, we can subtract that from the total stress and get the effective stress, and that gives us the effective stress parameters for friction angle and cohesion, and then we can use them to design for the long-term strength of our soil. However, as I said, what we're doing today is a quick undrained triaxial test, which is quite a quick test to do. So what does triaxial mean? Well, as we said at the start, there are three different planes under which stress is applied to the soil. In the horizontal plane here, we have the surrounding cell pressure pushing on the soil sample from both sides. So you might say that's the X direction and the Y direction. And that surrounding pressure, which we represent as sigma 3, our horizontal stress, represents the stress in the ground that is confining the soil that's being compressed, that's being stressed or loaded. So the surrounding stress here around the sample, represented by sigma 3, is the cell pressure. And we can change that to represent different depths. So for example, if you had a soil with a weight density of 20 kilonewtons per meter cubed and you were 5 meters depth, your vertical stress at that point would be 100 kilonewtons per meter squared. So you have a surrounding pressure of 100 kilonewtons per meter squared, 5 times 20. The other stress, the other axis, is the vertical axis. And this is represented by sigma V, or sigma 1, the total vertical stress, and is applied by the ram here. So what we're going to do is compress the sample to failure with a surrounding cell pressure, in this case, of 150 kilonewtons per meter squared, and then measure the amount of vertical stress. Initially we measure the vertical load, we'll convert that to a stress, and that will tell us the failure stress for the sample. Later on we will design or draw a Mohr circle plot to determine the friction angle and cohesion of the soil that we've tested. So let's go back to our sample. You can see here the sand is confined inside the rubber membrane, which I showed you earlier. However, to stop the water getting inside the membrane and wetting the sample, I've applied an O-ring seal at the base around the pedestal, and I've applied an O-ring around the top cap. And that means inside that sample, we check this at the end of course, it should stay completely dry. We're going to apply, quite shortly now, we're going to apply a cell pressure of 150 kilonewtons per meter squared. I've got a pressure generator here that's going to generate the water pressure, the water stress. There is a bit of a noise when I turn that on, so I hope that you'll continue to hear me clearly. And once that pressure has stabilized at 150, which by the way is just down here on the dial gauge, I'll set this dial gauge to 0, and this is the dial gauge attached to the proving ring that will record the vertical action, the vertical force on the ram that's applied to the sample. And I'm going to let the test run until the sample fails. So the failure is not a dramatic failure, it's not like a concrete cube crushing, for example. Instead, the sample will most likely, if it's properly constituted, simply swell to failure, what's called a barrel of failure. So you'll see it swelling, enlarging as the test proceeds. Now once the stress reaches a maximum, and notice the dial gauge here stops increasing, that's our failure state, and we'll stop the test and record that. So let's go ahead with our first sample. We'll turn on the pressure gauge here. I'm going to give it a minute just to come up to pressure, and we'll check that. You may be able to see the dial gauge here, it's moving as the water pressure comes into the cell. This water is now coming up to 150 kilonewtons per meter squared. The dial gauge over here has stopped. I'll just do a quick check. Yes, it's at 150. Check that this is 0. It's almost exactly 0. There it is there. So now the dial gauge is at 0. The pressure gauge is at 150. We're ready to start the test. We press run. Now you can see, I hope you can see, as soon as the test starts, you can see the dial gauge starting to move around. It's at 40 at the moment. This is the sample that's being compressed. How is it being compressed? The pedestal is being pushed up around the ram, effectively causing the ram to crush the sample. It's at 115 at the moment. The sample is still behaving properly. Let's just let it run and see how far it goes. It's just increasing very slowly now. It's at 330 and it's dropping back. I'm going to stop it there. It's at about 335, pushing towards 340. I'll hit the stop button. I'll turn off the cell pressure. So our first test carried out at a cell pressure of 150 kilonewtons per meter squared has resulted in a dial gauge reading of 335 divisions on the proving ring. We'll convert those proving ring divisions to a force later on and work out the stress on the top of the sample. So what we're going to do now is we're going to debench the sample. We're going to take it down and I'm going to show you how the sample was constituted. Then we're going to reform the sample for our next test and repeat the process. So what you take from the first test, write down the cell pressure is 1 equals 150 kilonewtons per meter squared. The second thing to record is the proving ring divisions at failure, and that was 335 divisions. Make a note of that. Or even record it on a video. Okay, you see our sample is unloading here. What we want to do now is to debench the sample, that is to take it down. So the first thing to do is cut off the water pressure at the tap here. The drainage tap here will let the water out, so I'll open that cell, that tap, oops, very violently. We'll bring down the ram, that's the ram here coming down, or the pedestal coming down. And also I'm going to open the air valve at the back, and that will allow the water to drain out. You can see how the sample has formed a barrel shape. And we have to wait for the water to drain out of the sample before we can debench it. drainage tap there, working away. The water level dropping. I've also the pedestal is going down, and that's giving clearance here, so I can easily take the cell off to set up the next sample. Press the stop button. Now the water has drained out. To take off the cell, we have 3 clamps. This is the first, second, and third. We'll leave them at the side for next time. Let's take a look at the cell itself. It's a cylinder, and you can see there it is, the perspex cylinder, which can be pressurized up to 2,000 kiloliters per meter squared, and the ram goes through a bearing at the top, a waterproof bearing, to apply the pressure to the sample. So we can set this aside. Now you can see the sample. It's not looking quite so impressive at this stage, and what we're doing with the sample here is removing it. And it's full of sand, so to remove it, simply going to grab the O-ring at the base here and roll it up, like this. Taking that out. I'm just going to use this tray. I want to show you that the sample is dry at the end of the test. Hopefully it is. There's the O-ring that was sealing the bottom of the sample. We'll just keep that to hand for our next sample. After that, we have a porous stone. This is here. This is to stop sand going through the pressure measurement holes at the bottom of the pedestal here. You'll see that again in a moment. And inside the rubber membrane we have the sand, and I hope you can see that there. That sand is completely dry. So we actually conducted the test on dry sand. To conduct the next test, I'm just going to take a moment to flush out or rinse off the membrane. There's the O-ring there at the top of the sample, and here is the next component, which is the loading cap. We'll see that going on again in a moment on the second sample. So excuse me for one moment while I wash off the membrane. Okay, so we're going to reuse the same membrane. One of the reasons we don't, we can, if we wish, of course, use a new membrane. That can be a good idea. But sometimes, once a membrane has been used in a test, it actually stretches more easily. It's easier to form a new sample in it. So how on earth do we form a vertical cylinder that we can compress out of loose sand? Let's have a look at how to do that. I'll leave the membrane there for now. So there's a number of steps in this. The first step is to seal off the base of the pedestal here. It's not visible on the video, but there are 2 drainage holes in the base of the pedestal, and I need to close that off, so I'll put this porous stone on top. A porous stone, by the way, is used to help measure water pressure inside the sample for a drained test or an effective stress test. But here we're just using to block the holes at the base of the sample. The next step is to take the rubber membrane, the same one we used in the first test. I'm just checking there's no sand inside it, because that could cause a leak. And then I'm going to put it over the pedestal, like this. And if it's in good condition, it should be possible to stand it upright like that. Now, at the bottom here, we don't want water to come up underneath the sample, so we're going to use an O-ring to seal off the base of the sample. And to stretch the O-ring so that it fits around the sample, I'm using this metal former, which we're going to use as a mold in a minute to make the sand sample. Stretch that O-ring around the metal former, but it's okay. It's sealed the second time. That's the O-ring around the base of the sample. Now we'll take our mold. It's a split mold called a split former that we're going to use to form the cylinder of sand, and we're going to place it around the membrane like this. I have a rubber band here which I'm just going to roll up, and that's got the job of holding the former together. And then what I'm doing now is stretching the rubber membrane around the inside of the former, and I'd like to get rid of any creases, because those, if there are creases, they will appear as creases on the finished sample, which is better to avoid. So I'm just checking for creases in the rubber. That's okay. And then I've got a cup of the same sand as we tested in the first part of the experiment. I'm just going to carefully fill that up. Just slightly overfilled the sample there. At this stage it's a loose sample, a very loose sample, so I'm going to tap the metal former to make the sand compress, to compact it together and make it stronger. While I was doing that, the level of the sand has settled down as it compacted closer together. I'll just top that up with a little bit of extra sand, like that, and again compact it. I'm being careful to ensure no sand spills down the side of the inside of the cell, because that could cause a leak later if it bridges the seal. Now I take the loading cap, which goes on top. It's a cylindrical cap with a dimple in it. Pop that on top. And this is quite a tricky part. We want to release the membrane around the loading cap without disrupting the sample. So you have to kind of, this is where you need about three pairs of hands would be helpful for this part. But anyway, we'll try. Excuse me. There you go. Now you can see that the membrane is surrounding the loading cap, and now I need to seal that with a second O-ring so the water can't get down through the top of the loading cap and into our dry sample. So to stretch the second O-ring, I'm just stretching it around a second former here that I have to hand, like that. That's stretched, and I've carefully fit that around the top of the sample. Like that. Now, having sealed the sample with the second O-ring, I will now fold down the membrane around the top cap, like this. And hopefully now I have a cylindrical sample of sand compacted into the membrane, and I can safely remove the former, and hopefully the sample will stand up by itself. Let's have a look and see. And now you can see the sample as a compacted cylinder, restrained within the rubber membrane, sealed with the O-ring on top and the O-ring on the bottom. We're ready to go with our second test at a higher cell pressure. So to set the cell up, here's the cell again. I'm just going to take the pedestal down, it's up a little bit high. And while that's coming down, just have a look at the cylinder. As I said, it's a perspex cylinder. Here's our loading ram. There is a valve at the top. This is an air valve to let air out while the while the cell is being filled with water. Okay, let's just stop it there. Hopefully that's enough. And this is a very tricky part of the experiment. It's very easy to collapse the sample accidentally while you're doing this. It's happened before. Yeah, I think we're okay. Hopefully. Okay, once we have the loading cap in place, we clamp the cell to make sure no water can escape. Okay, it's worth taking a moment to make sure those clamps are straight, because if there's any tilt on the cell wall, when you clamp it, water will escape from that side. We're about to use a relatively high pressure for this cell of 250 kilonewtons per meter squared, so I think we're good to go. Next stage, we're going to fill up the cell with water. Closing the drainage valve. This is a very stiff tap at the back there. Okay, let's have a look. Now the cell is being filled with water, and the air is escaping from the air valve here at the top, so when it's full, the water will start to come out there. Just make sure I can control that. Okay, so just closing the air valve and the cell tap there, the water tap. Now the cell is full of water. I'm going to bring it up to meet the proving ring. It's quite a big gap to close here, and obviously this pedestal moves very slowly, so it'll take a moment to get up to the level of the proving ring. This is an important part, because the sample is very weak now. There's no pressure in the water to hold it together. And if the ram comes in contact with the proving ring and loads it, it will just crush the sample very easily. So even though it takes a moment for the ram to come up, you have to pay careful attention when it gets close. So I'm just judging with my hand and also watching the proving ring gauge there. There we go. Stop it there. Good. Just drying up some excess water here, because I want to be able to see very quickly if there's a leak. Okay, next stage is to set our pressure. We're going to go for relatively high pressure of 250 kilonewtons per meter squared. So, just going to adjust that up. I've now set the gauge to 250 kilonewtons per meter squared. You have to watch very carefully for the possibility of leaks at this stage in the experiment. I'm going to now open the cell pressure to the gauge here. And you may see the dial gauge moving around on the top of the sample here. It's stabilized at 20 divisions there. Just check. Yep, we're good at 250. Now set the dial gauge to 0. And it took a little bit longer than expected there, because there was actually a gap at the bottom of the dial gauge there we'll have to fix. I think we're good to go. Just check it again. Okay, I'm happy with that, and we're just about holding up on pressure, so we go right ahead to test one last check on the water pressure. It's still at 250, we're ready to go, and we'll hit the run button now. We'll start loading straight away. It's under quite high pressure here. So now it's coming up to 200 divisions, 2 full rotations. We expect this to go further than the previous test, which was at a lower pressure. It's just going through 300. It's 400. It seems to be slowing down, it's not increasing at the same rate, which could mean, suggest it's coming to failure. It's just going through 500 divisions at the moment. And the dial gauge here, the needle on the dial gauge is slowed down a lot. So the soil particles are shearing over each other, they're moving and not increasing in strength. And inside of the sample, it's probably swelling as they move apart. Under the vertical stress from the ram. It's almost stopped there at 530, so we're probably at about, on or about the failure point. Yeah, just 540 at the moment. And I can actually hear the soil particles, the sand particles, scraping over each other as I stand beside the cell. So you want to get a reasonable estimate of failure. Sometimes it will continue to increase for some time, partly because of the resistance provided by the confining membrane, for example, the rubber membrane. But I'm happy enough really that we've reached the failure point on the stress strain curve. And I'm going to stop it now. It's just sitting at 560. So we're going to call the failure point today on this second sample as 560 divisions. So turning off the cell pressure there, you may be able to see, I'm not going to debench the sample this time, but it has widened or swelled a little bit to failure. This sample has also very slightly deflected. It mightn't have been quite vertical at the start of the test, and that would give a slightly lower test result. So that may affect our result. So what is this test result? Well, for now, we had the proven ring divisions representing vertical force at 560 divisions. Make a note of it. The cell pressure we set at 250 kilonewtons per meter squared. That's the confining stress. We call that sigma 3 or sigma h for horizontal stress. And those are the two values we take from the test, and we will use those to get our third test result later on to draw the more circles for this test and the graph of the failure line, and then from that we get our friction angle for the sand. So I hope that you're able to follow the lab demonstration here. We've tested 2 samples in short order. I've shown you how to prepare the samples, to put them into the cell, how we pressurize the cell, and then carry the test to failure for the quick undrained triaxial compression test.